Right. So for the lab second part, what we did was we wanted to indirectly measure the temperature of fire. So we measured it for real, just so we could tell in the end how far off we actually were. And we are going to be off very, very far, so don't worry too much about that. So our unknown is actually going to be the initial temperature of the steel ball. And if you remember, we held this steel ball in the fire for a very, very, very long time. Long enough to assume that the steel ball was about the same temperature as the fire. Which makes it a lot easier to determine the temperature of the fire. So, everything that we do know is written up here. You can mostly see most of it. It's a big mess, but we have the mass of the water in the calorimeter cup, which is set up just like before, where it's a hot thing being dropped into a calorimeter cup full of water. So we have 0.02563 kilograms of water. That's 0.2563 if you're writing this down. Then we have the mass of the calorimeter cup, which is 0.0604 kilograms. The mass of the object, in this case the steel ball, which is going to be 0.0279 kilograms. Then we are into specific heat. We have the specific heat of all of the objects this time. So we have specific heat of the object, the steel ball, is 470 joules per kilogram degree Celsius. And the specific heat of water, just like last time, is going to be 4,180 joules per kilogram degree Celsius. And our found experimental value for the specific heat of the calorimeter cup is 2,262.46 joules per kilogram degree Celsius. The initial temperature for the system of the calorimeter cup and the water in the calorimeter cup is going to be 19.03 degrees Celsius. And the final temperature, when the system reaches equilibrium with the steel ball inside of it, will be 27.35 degrees Celsius. So it obviously doesn't go up that much, but you have to consider the specific heat of the steel ball as compared to the specific heat of water. It's about 1/10 the specific heat of water, and it has significantly less mass than the water. Well, actually, it's not significantly different. It's actually just a little bit greater. Not enough to matter. Not 10 times greater, so proportionally it doesn't change anything. Alright, back at it. So we expand it out again. For Q, we're subbing in MC delta T. So mass specific heat, change in temperature. And change in temperature, of course, is T sub F, so final temperature, minus T sub I, initial temperature. And T sub F is going to be equilibrium, so for every object in the system, it's going to be the same. It'll be 27.35 degrees Celsius. And it is, the initial temperatures are unknown here, so this is going to be a little bit different to expand than in the last problem. But for the object, we have 0.0279 kilograms times the specific heat, which is 470 joules per kilogram degree Celsius, times 27.35 degrees Celsius minus Ti. Now we're going to be able to multiply these, but we can't distribute them without making the problem more difficult for ourselves. So we won't be doing that in the next step. I'll pause the video for a minute so I can put the actual values down, probably. Anyway, we have, for QH2O, we have an M of 0.02563 kilograms times 4,180 joules per kilogram degree Celsius. And then we have our delta T, which is going to be 27.35 minus 19.03. Both of those are in degrees Celsius. So, we've got our mass for our calorimeter, our found value for specific heat of the calorimeter, which again is 22.62 joules per kilogram degrees Celsius. And then again our delta T, which is actually going to be the same as it was for H2O since they were the same system. 27.35 minus 19.03. So I'm just going to write those values down on the board here right under it. Again, these are all going to add up to be 0, which is why it's so easy to solve for the initial temperature of the steel ball, which should be the same as the temperature of fire, but won't. Just to reiterate, this is not a very successful lab, and I don't think it will be for anyone, so don't worry about it. Alright, so this bit here, this first part is going to simplify down to 13.113 times the quantity of 27.35 degrees Celsius minus T sub I, the initial temperature of the steel ball, plus 891.3499, which is this guy simplified, plus this guy simplified, which is going to be 1,136.9495. And again, all of this is going to equal 0. So if we add these two up, we can subtract them from the 0. So that's just some basic algebra. Most of this video is totally unnecessary except for to try to prove to myself, more than anyone else, that my math is not very wrong. So what we are going to end up with then, and I'm just going to erase what's above it here and write a little bit backwards. What we end up with is going to be that 13.113 times 27.35 minus Ti equals negative 2028.2994. And we could distribute this in and then have to subtract those two from this side and then divide by this number. But that is annoying as hell. Alright, algebra. So what I did was, to carry off from where we were just a minute ago, I divided by this 13.113 to simplify this side so we can eventually isolate T sub I. So that produced negative 154.6785, from which I subtracted this 27.35, so that's gone on this side. And since these are two negatives, I got negative 182.0285. And because of the way the problem was set up, I got negative equals negative, so we all know that equals a positive, but we have multiplied by negative 1 is obviously going to cancel all of your negative symbols. So you have T sub I will eventually equal 182.085, or 0285, sorry, degrees Celsius. You can't see where I just added that. Degrees Celsius. It looks kind of like an E. Anyway, that is terribly far from what the actual accepted value our measured value for fire anyway. And we could probably stand to calculate that error right here. And for our error analysis, we can consider some pretty basic stuff, like any imperfections in the steel ball would throw off the value of C that we use, or whatnot. Be creative. Whatever you want to pretend it was can be what it was. Just a minute. Just for funsies, let's see how far we really were off. So we have the measured value, which we're going to call the real value, which is 1,290.02 degrees Celsius. Let me rewrite that so that it is legible. And we're going to take that accepted value minus our very small found value, and then we put it all over our accepted value again. And then we'll multiply by 100, I guess, so just in case you don't understand that for some reason. Which is going to be a whopping 85.889% below. Which is not even remotely close. We are off by like 86%. Don't beat yourselves up too much. Anyway, if you saw a problem in my math, I welcome you to inform me. I'd like